Good morning, everybody. How are you doing?
Pretty good today.
Nice, that's good. Have a good weekend. All right. Let's see. Looks like we got just about everyone here. And it's 8. So let's get started. All right. So today we'll be looking at homework 3 some more. As far as other announcements, just wanted to show you one thing that I posted. So this is something that I posted on Friday, and this is a method for solving for the electric field of an annular ring that's centered in the XY plane, and you find the electric field at some point on the Z-axis. This is pretty similar to one of the homework problems, and this is also a classic electromagnetics problem. You probably solved this in your physics class in one form or another. But this solution that I have here, let's see if I can zoom out just right. It shows how to do it using the cookbook method. Okay, so you're welcome to take a look at this. I think we'll probably revisit this problem in homework 4 when we look at the electric potential. But it's also similar to one of the problems in this homework. So I wanted to show you that this was posted, so feel free to take a look at it. There is one thing that I want to point out. So this cookbook method that I've shown you works really well when you're in Cartesian coordinates. And when you are solving problems in other coordinate systems, there are a couple things to note that sometimes actually force you to switch back into Cartesian coordinates. And so if you look through this problem, you will see that I have actually switched to the Cartesian coordinates. All right, so anyways, this is on Moodle. We might talk about it a little bit more today when we get to that other problem, but I just wanted to let you know that it was up on the page and you could scroll through it and get to this solution, which is the classic solution, and is also, this is one of the examples in your textbook. So if you're reading through the textbook and want to see a second way of solving this problem using the method, this cookbook method, then you can find that here. Besides that, we're just moving right along with Coulomb's law and electrostatics. We have a couple weeks left of this, right? So in the class, we've already gone a few weeks. So we're here in week 4. So we're going to spend week 4 and week 5. So this week and next week are all going to be continued on with the electrostatics. We'll basically look at almost everything, every topic in the textbook in chapter 4. And then we will have a day of review on the 28th, and then September 30th is exam 1. So just that's coming up on week 6. Does anyone have any questions about this class or the schedule or anything that you want to ask?
So for the exam, are we expecting like just the math problems, like the ones we've been doing in the assignments?
Yeah, like from here, from that first.
Yeah, from the vectors.
There could be a math problem that is related to this, the first stuff. If there is, it would probably be presented in the form of find the find something that has to do with the electric field, right? So find the divergence of the electric field or something like that. And how does that relate? Because we'll see as well, right, that the coming up that in the next homework, that the electric scalar potential and the electric field are related in that way. So there may be some things that we consider. And then also when we're in electrostatics and there's no time variance, things like the Stokes theorem will hold. So there are concepts from the first homework assignment of the mathematics that I might ask a question regarding, especially because the stuff in assignment 1 we'll be using throughout this course. But it would, the main things are the electrostatics. All right, any other questions? All right, let me see. For some reason, my here we go. All right. I have a stylus pad that I draw our notes with. It was not connecting to my Bluetooth, but I just got it, so I think we're all good here. Okay, let's go on. Show the notes. And let's take a look at another Coulomb's law problem. Yeah. All right, so take a look at this other Coulomb's law problem. So this one says there's a line charge, and the line charge has uniform density. So the line charge has this uniform density in microcoulombs per meter. It exists in the air. Okay, so when we're doing electromagnetics problems, we talked about this just a little bit last week, but remember this rule, okay? That if we see something that says in free space, or in air, Okay, so whenever you're reading a problem and you see in free space or in air, that means that the dielectric permittivity, which we know takes this form. If we see one of these things, this means that the relative permittivity is 1. All right, so we can say that epsilon is equal to epsilon naught, which is 8.85 times 10 to the minus 12th farads per meter. Okay, so when you're reading through a problem and you see something that says in air or in free space, which I think the last problem said, then know when you get to the part of the problem where you're solving and you need to choose an epsilon, you can choose the epsilon, the constant epsilon. All right, and that's because the relative permittivity of free space or air is equal to 1. So this is in air on the z-axis between z equals 0 and z equals 5 centimeters. So in this problem, what I want you to do is find an integral expression for E at a point even higher on the z-axis. So use the cookbook steps to come up with an integral expression on the z-axis at 10 centimeters. And then in part A, do not solve, okay, do not solve the integral.
Is it 10 centimeters for z-axis or y?
Oh, pardon me, yes, thank you. It is on the y-axis. X, Y, Z. Thank you for that. So find it on the y-axis. And then in part B, do use something, some tool to solve this. So whatever tool is your choice. To solve. All right, and the reason that I have this broken into 2 parts and I have it set up this way is that there's this important thing that I want you all to realize, and we've spoke about this just a little bit in the class, but sometimes in electromagnetics, right, we have these 4 Maxwell's equations, and they're very complicated equations, right? They're all vector calculus, and as it turns out, right, we've looked at this method for solving these some of these for the electric field analytically, right? We can do it by hand, it's no problem. But sometimes it's actually going to be too difficult to do that by hand. And sometimes you might even arrive at an integral expression that's not actually solvable, right? So you probably, in your calculus class, did you talk about integrals that cannot be solved? Did you talk about that? Yeah, so there's, okay. You are familiar, or no, you're not familiar?
I'm not familiar.
Yeah, we did learn some, but I don't remember what they
Okay.
are. That it was too hard. It was too complicated for our calculator.
Yeah, and so that's just reality, right? Some integrals are too complex to actually solve. You can't, there's no analytical solution to it. So when there's no analytical solution, though, you all remember doing Riemann sums, right? You can do a Riemann sum and approximate the answer, and that's a numerical technique for integration. And so the distinction that I want you to see is that electromagnetics is a field where you end up with integrals sometimes that are just too complex to actually solve. And in this case, you could, if they're too complex to do by hand, you might be able to get something like Wolfram alpha to solve it, which is the case this time. But if you do an even more complicated one later for some reason, like outside of this class, you would probably need to use MATLAB or do something like a Riemann sum approximation to actually solve it. So this is just a real life place where you might come across a difficult integral expression, and that's why this problem is broken into two parts. One, which is the level of integration that you could expected to do in this class, which is you can always set up the integral. And then part B is actually solving the integral. So there will be some times in this class where arriving at the expression, so just, and when I say expression, right, all that would mean is something like E equals, this integral, something like this of your DQ. This would be your integral expression. So there may be some times in this class where the final answer is going to just be an integral expression because we won't be able to actually solve it. All right. So I will give you some time now. So pull out the Coulomb's Law cookbook and see if you can solve for this integral expression for this line charge. All right. And I will also put you into breakout rooms so you can work with someone else on this and use that Coulomb's Law cookbook here. And then I will come through the rooms in just a moment. All right, how are you both doing?
Good.
All right, so are you using the cookbook right in the RS? Is that what you're doing? How's that going?
Yeah. So
Okay, any questions?
just at the end of the day, is your for this areas, choose something like CS represent the C component of the source. So that's the integration variable.
Yeah, I'm having a bit of trouble understanding you, but I see in the I agree. So it's in the X direction and the Y direction, right? Our vector has 0. And then in the Z direction, we should choose Z to be some variable, right? So it'll be some, yeah, like that. Yep, that looks good.
So
Perfect.
The DL would be into DC as direction.
Yep, yes, yeah. Yeah, so in this case, yeah, when we are on that line, yeah, we will get the DL will just be DZ. That's totally correct.
It's also the same as ZS, this variable here.
Yeah, so yeah, we will it be the same or will it be different? And we know that the charge is actually along that. So I believe that it should be the same Z variable. So it'll either be your DL would be ZS or yeah, in your case it would be ZS. Because we are integrating along where the source of that charge is.
Thanks.
And so that's part of what is going to, once you get to the end of this, that's part of what's going to make this a difficult integral to solve. All right, AK, any questions?
No, not yet. I'm still going through it.
Yeah. All right. All right, well, I'll go to the other room. All right, how are you doing? Any questions?
My question is, since we have just one point, does the source RS become like the origin?
Yeah, I think I understand what you're saying. So does the origin, I would still choose a 0, 0, 0. That will be the most convenient origin. Now, I think maybe the other question maybe you're asking is about the what you would integrate over. Is that like?
No, your first statement answered it, because we have to subtract the point from the source, and it's easier when we have like point charges all over, but this one we just have the one
The line charge.
Yeah. So what I would, when you are making the vector RS, you'll have to choose some variable and about where the charge is in the Z location. So we know, right, for RS, it's in, if you write a vector from the origin to the source, in X it's 0 and in Y it's 0. But in Z, we have to think, right, okay, where is that charge? And so it's somewhere on the Z axis. So we can assign it a variable. we'll say it goes to write a vector from the origin to the source of the charge. It would be in the z hat direction, it will be z, some variable amount z. And that variable amount we know is constrained between 0 and 5 centimeters. So I'll just assign that a variable like this, and I'll just assign it a variable so that from the origin to the source, it's some variable z. And later, when you choose the DL, right? So you're going to need to choose some DL that you're going to integrate over. And that DL will it will integrate over this same Z, right? Because we are going to need to choose every little bit of charge along here, and we'll need to integrate up that amount of charge. Does that answer
Yes,
the
it does.
question? Okay. So this variable is the variable that you will integrate. So you could also, if you wanted, you could choose, maybe you could write it as ZS, and then you could choose a DZS later. But just, remember what we're doing, it's this cookbook, right? We're trying to solve for some DQ, and the DQ is saying we should add up all the charge, right? So in order to find the DQ, it's okay, we're adding up all of the charge. So we need to integrate over the charge, wherever that charge is at, the source of the charge, we need to integrate up all of that.
All right.
Okay. All right. Well, I'll leave the room and let you guys work on it a little bit more.
Is it going to be a double integral or just the one for the line charge?
Yeah, good. Another good question. So let's take a look at this cookbook. And on the line charge, so when we have just a charge, a line charge, basically these are just charges that are all in a line somewhere. And so they will all be covering one of these. You would select the DL from this set. So you'll only have one, you'll have just DX, DY, or DZ in this case. Yeah, of course you could do something, more. We won't do that. We won't do it in this class. If your charge, like, let's say, you had something like this, and these are your charges. This is the line charge.
Mm-hmm.
Then your DL would be a little bit more complicated, right? You would have to choose one for here, break it up into two integrals. We won't do that in this class, but it is possible to do that. But in this class, we're basically going to be dealing with line charges that are, just they're conveniently on some axis for you, is what we'll be doing. Yeah. So nice question. Thank you.
Thank you.
Any other questions?
So after we find the line charge, I'm just confused where it says at that point on the y-axis. Is we're integrating at that point.
Yeah. Okay. So yeah, let me share another screen. Okay. So remember our discussion on superposition, and we said, okay, when we have these charges, we can treat them like a superposition where we add them all up. So the sum of all these individual charges, right, would give us one full amount of charge, a full electric field. So if we have this as our line charge. All right, so this is our line charge along Z. And we're looking at the point, right? We're looking right here. Let's break this up, okay? And let's say, you know, this little bit of line charge, right, is going to exert a field here, all right? Now we're going to keep integrating, right? And this little bit is going to exert a field like this. This little bit, right, is going to exert a field like this. And so on and so forth until we get all the way up here, right? And this one's going to exert its electric field. So these are all electric field, and I'll call this, so this one is electric field at Z equals 5 cm. And this one is the electric field at Z is equal to 0 cm, right? So we have all these little ones added up, right? And so the total electric field is E at Z equals 5 cm plus blah, 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 right? All the way up to the electric field Z equals, oops, sorry, this should be 0. So that this integral this is what this is doing. It's just doing a big superposition for you of all these little bits of field. And that's why your DL should be this DZ. Does this clarify things a bit?
Yeah, I think so. And
Okay.
just finding all adding all those vectors together that are on that point. That's where I guess I have to find out if my integrals right first. I just have 0 to 8 and then the 8 microcoulombs per meter for the density dz.
Yeah. Yeah. So the integral that the cookbook, the cookbook will give you this integral. Which is the same as doing this.
Yeah, okay.
So this is the hard way, right? The hard way is, so just like before you knew calculus, the hard way of getting, you know, you could do the Riemann sum, right? This is like almost like the Riemann sum or something. This is the hard way where you look at each little bit and sum it together. But the integral is the easy way. And the cookbook kind of walks you through how to set up this integral. But because electric fields do follow the law of superposition, it's feasible, or it's possible to do it either way. Yeah, and you could even and it's, as electrical engineers, right? We know, this is jumping a little bit ahead, but we know that charge is actually discrete, right? Like the smallest amount of charge that exists is one electron. So technically, right, a line of charges would just be a bunch of electrons that were in a row. So in some senses, this discrete method is also true. We don't need to get too out in the weeds on it, but these are both, you could think of them either way as being correct. But the mathematical tools tell us that, we can integrate to arrive at the correct answer. And that's usually going to be easier than finding the electric field due to each individual charge.
Mm-hmm. Okay. Makes sense.
I know this stuff gets a little crazy because often in real life, you don't solve problems like this, but it is like also the foundation for understanding how the individual charges create fields. And possibly if you end up working on circuits or microelectronics, you might really be working with so little charge that it might be convenient to think of it more from this very basic perspective, like going more back to a pure physics standpoint.
Mhm.
But not every job would do that. If you work in power, well, even that you might eventually find some problem where it's convenient to think of it from this, of this fields theory. But it's often this stuff is something that if you go into certain specializations, you might think about more regularly, but it can, it's important to know that it exists, but it's not everyone would end up using it.
Okay.
And I think too, the way this class is structured in the later part on transmission lines, that stuff is much more applicable. So the last section on transmission line theory, people who work in microwave engineering use that those equations all the time. Like that stuff is much more common to see in actual microwave circuit design, whereas the electrostatics and is much more of a theoretical. It tends to be more on the theoretical side. So,
Okay.
all right, any other questions? All right, I'll let you work on this for a little bit longer. If you get to that final integral expression, you could go to Wolfram and see if you can solve it there as well. All right. So was anyone able to get to the final integral expression? Were you about to share yours, Gabriel?
Yeah, I think it got up. I got something.
Okay. Yeah, okay. So the final expression that I got looks like this. Did anyone else get this down here?
Yes.
Okay. All right. So some of the things that I got asked, I think, were what should this be? And this should be a variable. Okay. And then down here, you should integrate over the variable. Okay. And the variable. And the reason that this makes sense, all right, let's think about what we did. So this variable that describes the direction of the electric field, right? So this one, this is a vector that describes the direction of the field, what direction the electric field is going to be. So remember, we're trying to find E at this point, and this RSP vector describes the magnitude and direction of the electric field at that point. And so we can see, right, that it's going to be in this y direction. And it will be, it'll have some component in the y direction, 0.1 in the y direction, the magnitude in the y, and then in the z, it will have some magnitude, some negative magnitude in the z direction. And that makes sense, right? Because our line of charges is up here. And so if I chose some point here, some part of the charge, and determined what it was down here, we can see, right, that this total bit of field is going to be in the positive y direction and in the negative z direction. So it makes sense, right, that this RSP vector is going to be pointed down. And no matter what the z is, right, even if we chose it here, right, we can see it's the same thing, right? It's going to be in the positive y direction, and it's also going to have some negative z component. So this RSP vector is a variable vector, and depending on where we are in this line charge, the electric field due to this part of the charge is going to be pointed in the positive y. It's going to have a positive y component and a negative z component. So this is that final answer for B. Okay. So I'll leave it to you to go into Wolfram and do this integral and get to the final solution. Sorry, yeah, do we have a question?
Yes, with Wolfram, I'm trying to put in the vector signs. I don't know if I'm just not finding it, but like, do we need to put those signs in or not?
Yeah, that is a great question. Thank you, Danielle. So let's think about this. And actually, we do not need the vector signs. And there's actually even one more thing is how many integrals do you think that we could break this into?
You could do a y and z integral
Yes, yeah, so
too.
that is absolutely correct. That will be the easiest thing to do here. Let's see, is actually to break this down even further. And we could have two integrals. One is in the y direction. And then the other one would be in the z direction. And I have just enough space for it. So like this. So to answer your question, Daniel, yeah, the vector, these vector components, right? This tells us a direction, right? And this is not a variable, right? These y hat, z hat, these are not variables. You don't actually integrate them. All these serve to do is you could think of them as a placeholder for saying, okay, I will do this integral of all of this stuff, right? And all of this stuff is going to give me the final magnitude, right? And the direction component is separate. So the direction component will be separate. So this is just a placeholder to say, okay, we know that we have a direction, but we still have to find the magnitude. And the magnitude is the integral part. No matter what the result of this integral is, it will still have the same direction. It will still have the same directional component. And no matter what the integral is, no matter how we solve the integral, this will end up being a scalar by itself that will just describe the magnitude or the amount of the vector that is in this y direction. And so we just keep these y hat and z hat separate. We leave the little hats on them so that we know as a placeholder that that's the directional component, and we don't need to take those into the integral. And so because of that, as Cade pointed out, right, this is a convenient one to break into actually two different integrals because we have the two different directions. Okay. All right, any other questions? Yeah. So let's see here. All right. So I think for question 4, that one is very similar to the problem that I posted. So that one's very similar. The way to solve question 4 is very similar. So I will leave that one to you to do. I'll give you a couple tips though before we move past it. So we have this one. It's located on an arc. Now, if we go back to the solution that I posted for you, in this solution, I integrated from 0 to 2 pi. But in your solution, Let's see here, make sure. Yeah, there's a couple different ways to do this, but you will also need to integrate from, instead of integrating from 0 to 2 pi, you would need to integrate to pi fourths. And also, you will need to include the other vector components, which are further up here. You will need to use this whole this part. All right. So this, when you get down here, you have this dE, and and this is the full expression for the electric field. And so when you go to integrate this, you will need to integrate from 0 to pi fourths. Okay. So this is for the full ring. And this
I don't think we can see yours.
oh,
Your
sorry. Thank you. Thank you for pointing it out. Okay. So this result, this can you see the notes? Okay, so this result is for the full ring. This is on Moodle. But for this quarter of a ring, you will instead need slightly different ones, and this is for this quarter ring. Or actually, this is even not even a quarter ring. This is an eighth of a ring, eighth of a full ring. So to solve this integral, you will probably need to use some kind of software to complete that full integration, because it's going to be a little bit tricky to solve. All right, so when you go to this problem, you can look through the notes that I gave to show you how to do a full ring, and just know that the main difference is going to be for an eighth ring, you will just need slightly different integration limits. Okay, slightly different integration limits, and you will need to evaluate at different heights. Okay, so so the full ring, we have H. We have H as some point on the z-axis, so 0, 0, H, and so H is equal to 0. H is equal to 0.5 meters, and H is equal to 0.5 meters. Make sense? Okay. Oops. Now let's look at question 5. Of the homework. All right, so this is question 5 on the homework. You're given an electric flux density and you want to find these different things. You want to find the total volumetric charge density, the total charge enclosed in the cube, and then then you want to find the total charge enclosed in the cube using two different methods. So we have the differential form of Gauss's law, the integral form of Gauss's law. You could use either one to find the total charge Q. So on your paper, find the divergence of this vector. Okay, so we are given the electric flux density, and we can find the charge density by taking the divergence of this electric flux density. So on your paper, see if you can find this rho v by applying this equation. All right. And then once you've done A, I think B should be fairly fast. So once someone has A and B done, let me know and upload it to the Google Drive, and I will share it. So let me know when you have it finished and uploaded A and B to the Google Drive. And then if you need a hint on part B, just remember that we can do a volume integral, right? If you have the density of something, you can integrate the density over a volume and arrive at the total amount. So if it's a charge, you can integrate the volume charge density over the volume, and you can get the total amount of charge. Okay, so can someone, even if you haven't finished, can someone upload the work that they've done already? So whatever work you've had, just go ahead and upload that now. Great. All right, so who else? Who else got this result? Give me a thumbs up if you got this same result. All right, Gabriel.
I-
AK, what did you get? AK, what did you get for the divergence?
Yeah, I get the same 0. I was trying to upload it, but
Okay. And Danielle, did you get 0 for the divergence?
Yeah.
All right, so yep, this should be correct. All right, so for part B, what is the result going to be, right? So if we're doing this integral, what is this going to be? First of all, what is this?
That's
avoid
0, right?
basic.
Yeah, you just found it. It's 0, right? So what is this full integral going to be?
0.
0.
Yeah, this will also be 0. So what in part C, what is part C going to be? What should that be?
0.
It should also be 0, but it's a little bit harder to get because you'll need to do a summation of integrals. So there's 6 integrals that you'll need to do to finish part C. And that is going to be a integration of the surface for each one of those. So when you go to your cookbook, right, you'll need to choose the ds for each different side of the cube, right? So each different side of that cube is going to have a different ds that you'll need to choose. And you'll need to choose each one of those ds's. Let me put them all over there. So you'll need to choose a different ds for each side of the cube, right? So you have this cube in space. Right, so this surface, right, on this surface, when you move around on that surface, right, this is going to be dy dz. When you move around on this surface, right, your ds is going to be a dx dz and so on. So you'll need to do 6 different integrals of this d dot ds. So, and you will also need to include, right, on this one, this is y, and this one is x. So when you take the dot product, right, you'll get a scalar result, and the summation of these should be equal to 0. Okay, so I know that we actually we're not able to get to the final Gauss's law problems. So I'm going to change the due date of this homework to next Tuesday. All right, so this homework will be due next Tuesday, as well as the quiz. I'll send out an announcement about this. So plan on first thing on Thursday, we will look at some of these Gauss's law problems. And I will probably, I may make depending on how far we get next Thursday, I may make a short video about how to solve some of these Gauss's law problems as well. So everything will get pushed back to, let me make sure I get the day right. But the homework is just going to get pushed back until the 21st. All right. So we'll finish up looking at this on Thursday so that you can hand it in next week. Does anyone have any questions? All right, then I will wrap class up a little bit early. You're welcome to take off. I'll stick around for a few more minutes if you have any questions, but have a nice day.
Thank you. Have a nice one.
Thank you.
See ya.
Bye.